Okay, so last lecture, last topic for the term. So what we've been talking about for the last several weeks has been optimization, which is how can we ensure that by building a model with some assumptions in it and so forth, that we can make optimal decisions or decide on optimal values for some inputs to that model to achieve some sort of target objective, minimizing cost or maximizing profit or something like that. Okay. What we've not really handled is, or not really talked about, is in building these kinds of models, you have to make a lot of assumptions and you have to sort of define mathematical functions to represent the world. Okay, you have to sort of represent everything as a function of those decision variables. But there are cases when maybe there's things we don't know for sure, where we're not sure about a value to put in the model or so forth. Now, in part, we've handled that with something called optimization sensitivity, where we've asked the question, if one part of the model, one parameter of the model varied with some different values, how would we re-optimize, and what target objective value would we come up with under that scenario? Okay. What we're going to talk about tonight is sort of a more generic way to handle when we're uncertain about things, or when we don't know how to model certain aspects or what values to use for certain aspects of that model. Okay, and that's something called simulation. So, where we've been trying to find these optimal values, there's something we've not handled, and that is uncertainty. Okay, for example, the example we just did, where we were sort of deciding on order amount or order quantity, but we assumed we knew the fixed cost, we assumed the holding cost was all known, that those were values that were predetermined, that we were certain of. We could use optimization sensitivity to ask, what if one of those parameters changed? But there are some cases where we don't even know necessarily what a good value would be. Okay, maybe we have an idea of a range of values that it could take on, and maybe that's true of more than one of the parameters of the model. Okay, so uncertainty, usually we'll talk about uncertainty in the values that we use in the parameters to that model. So for example, here we're uncertain of the exact cost of producing one unit of the product. Okay, so maybe we have to buy material to build a product, so that's a cost we pay to sort of build or make the product, that we're going to turn around and sell the product for a profit. Okay, but that exact cost is unknown. Maybe it depends on buying material like wood or metal or paint or any number of other things that we're uncertain what that cost value is going to be in the future. That is, it could change from what it is today, or we just may not have any data available to say what the true value would be. So those costs can fluctuate, they can change, they may just be unknown. All of this leads to uncertainty. So we can't build a certain model with mathematical functions if we don't know what values to use in those functions. Okay. So what we're going to do is use a technique known as simulation. And simulation works by saying, let's assume that these parameters to the model are random variables. Okay, that is, we don't know what value they will take for certain, but maybe we have a definition of a range of values they can take on. But what value they take is going to be sort of at random. That is, we can't predict it. It's not known. Okay, and we can do that with one or more than one of our parameters. And then what we can do is say, let's choose a random value in the range that we specified and execute the model with that value, and then choose a different value for these uncertain parameters and re-execute the model and choose new values for those uncertain parameters over and over again. That's called simulation. So we're simulating the model running with lots of different parameter values. Okay, and then we're going to show how the objective function, so whether we're trying to achieve a better profit or lower cost or whatever it is, we're going to show how that objective varies with the varying parameters to the model. Okay, so the model parameters are going to vary based on these random variables or random values we're going to choose. So the output, the objective, is also going to be somewhat random. It's going to have some built-in variance, which says here's the different range of values it could take on based on the range of values these model parameters can take. Okay, so let's do a quick example. So here we have a store, Butson Stores, and what they do is they sell some product, okay, and they have to use the sales that they make from last month to sort of cover and pay the costs of materials they buy for the product they're going to make this month for selling this month, okay. But the problem they have is keeping enough cash, keeping enough money on hand that they can pay for the material they need today solely based on maybe the sales they made last month. So if they didn't have a good month of sales last month, but they need to make more product, maybe the demand is going up, they need to make more product this month, they need to make sure they have enough money on hand to buy what they need to buy. Okay? So each month they have to pay certain fixed costs and taxes as well as material costs, and we'll say that those run at about 80% of the sales value. So basically whatever they sell something for, they're having to pay 80% of that in costs to build it. So there's a 20% profit margin. So they have monthly cash receipts. So they sell something every month, they sell product, and those are revenues that come in, but they don't get money until the following month. So they basically sell today, and through invoicing, they get paid a month later. Okay, as well as they also get revenue from a 0.5% interest on their short-term cash. So whatever cash they have on hand, extra sales from last month and so forth, they can put in a bank account and get 0.5% of interest. Okay, the company. So we're going to work over a 6-month period. So they enter this 6-month period with a cash balance of $250,000, and they want to make sure every month they have at least that much, $250,000. They also know how much they sold by the end of last month, December, which was $1.54 million. So they have sort of $1.5 million of income from last month that's going to come in. They've started out with $250,000, but now they're going to have to pay in January the fixed costs that they owe, plus the material costs for how much they want to build or make or produce to sell in January. Okay, so continuing on, if they finish a month with less than $250,000, that is, after they've paid out all their expenses, brought in all their revenues, they want to have a minimum of $250,000. But if they end with less than that, then they're going to take out a 1-month loan that they have to pay back next month with 1% interest. Okay, so they need to make sure they have enough cash on hand to cover just daily activities and things when they need to buy anything with overhead or anything for the office and so forth. So they want to make sure they have enough on hand so they can take out these 1-month loans as necessary. Now their marketing department has made estimates, so the marketing department thinks they know how much of the product they can sell for the next 6 months, month by month. But obviously those things are uncertain, so they're not projecting a particular dollar amount. What they say is, we think it will be in some range. That is, we have an expected amount plus some standard deviation, sort of a distributed random value that says we think it's this, but it may be up to more than that, it may be less. Here are the values. Here's the ranges. Okay, so we will be given those, and so given that uncertainty, we want to know basically 3 things. 1, how large is the maximum monthly loan likely to be that they're going to have to take out? That is, across the next 6 months, what's the month that they're going to fall short of their $250,000 minimum cash amount and have to get a loan for. So what's that maximum loan amount across the next 6 months, and how likely is that loan amount going to be that it exceeds their credit limit, so they can only get loans for $750,000. Are they ever going to need a loan more than that, or do they think they will ever need a loan more than that? And then finally, how much are they going to have to pay back interest-wise on the loans that they take out? So again, so we have parameters set up here, but mainly the main problem is we don't know the future. We don't know how much we're going to sell. All we know is some random distribution of what that sales number might be. So we have a mean and a standard deviation. And then we know the fixed cost that we'll pay for the next 6 months. Okay, so here's the values we're given for that. So we're going to go into Excel. We're going to start building this model. So I've already set up an Excel spreadsheet to aid in that, with a lot of these things entered in. Okay, so this ought to summarize pretty much what we saw on the table and the slides, as well as the text description. So we know how much we sold in December, right? That's a fixed number. For January through June, we have an average sales amount and a standard deviation, saying, well, we might be above or below that average, or above or below that expected sales amount. And for each month, we have a known fixed cost tax amount that we have to pay. Okay, material costs are 80%. We get 0.5% interest back on the cash we have, but if we don't have enough cash and take a loan out, we have to pay that back with a 1% interest. Okay, and we start January with $250,000, and we want a minimum every month of $250,000. Okay, so let's start building the model. So we're going to have our calculations section here. So I'm just going to use these same columns for January, February, March, April, May, and June. Okay. So the first thing we'll calculate is going to be the sales numbers. Okay. So we had projected sales numbers. We're going to have to simulate what the actual sales number is. I'm going to come back to this in a minute, but for now, let's just assume that our average or our mean sales are accurate. So let's just assume if we sold the same amount as the average numbers from line or from row 3 up here. Okay, so we'll make those currencies. Okay. So now we can start computing. Once we know how much we need to sell, we can compute cost. So if we think if we're projected and we think we're going to sell $1.8 million in January, we've got to pay 80% of that in material costs. Okay, so let's compute material costs. So that's just going to be 80%. I'm going to make that a absolute cell reference. 80% times the sales number. So 80% of the sales are costs we have to pay. Okay. We also have to pay fixed costs. Okay, we know what those are, but I'm going to go ahead and just copy those down so that you can see them side by side here. Okay, so we have our material costs, we have our fixed costs. Material costs are computed, fixed costs were just given. Okay. Now, what we need to compute is the revenue that we're going to have coming in. So the revenue from sales are basically going to be the sales number we had from last month. Okay. Okay, so I'm going to copy December sale number down here so it's easy to refer to. So in January, we'll have December sales come in as revenue. Okay, in February, we'll have January's sales numbers come in. In March, we'll have February's, and so forth. So that amount comes in. We need to know our beginning cash amount. Okay, so we know in January at least that our beginning cash is $250,000. Okay, and the reason we need to know that is because we also have revenue that will come in on our interest on our cash. So if we take the cash amount we have starting in January and multiply that by the cash interest rate, okay, make that an absolute cell reference, then that's more revenue. So in January we have December sales numbers. We get paid for our December sales. We also get interest from our bank, basically on all the cash we had left over at the end of December. That is the amount of cash we had coming into January. Okay. Now, I don't know yet what the February beginning cash is going to be. We'll get to that in a second. But you can see that I'm going to set up this pattern where I have my revenues from sales, my revenue from cash interest. Okay. And basically what we need to compute is of our revenue that came in minus our costs. Okay, so we have revenue come in from sales, revenue coming in from cash interest, and we have material costs we have to pay, so minus those costs and minus the fixed costs. Okay, I'm sorry, I left out one amount. We also have the beginning cash we have at the beginning of the month. So our beginning cash plus our revenue from sales plus the revenue from cash interest minus the two costs, material and fixed costs, okay, leads itself to how much cash will we have at the end of January. So how much money did we start with plus how much money came in January minus how much money we had to pay out. Okay, and the key is if this value is less than the minimum amount of cash we want to keep on hand, then we want to take a loan out. Okay, so now we're projecting in January, we'll end January with $101,000. Okay, these are thousands of dollars. $101,000, which is less than the $250,000 we want to keep minimum. So we need to compute a loan amount, okay, that we need to take out. And the way I'm going to compute that loan amount, you can do it a few different ways. I'm going to use the max function, okay, and basically say the max between 0 and the difference in the minimum cash we want and the amount of cash we suspect we'll end with. Okay. So if we want $250,000, but we think we'll end with $101,000, then the difference between that is how much loan we'll need. If that value happens to work out to be negative, that is, we think we'll end revenues minus costs will be more than $250,000, the max here basically just says we'll just take a 0 loan out. Okay. In this case, January, we think we'll have to take a loan of $149,000. Okay. Now, I didn't leave enough room. I'm going to insert one more row because there's now one more type of cost that we may have to pay back, which is loan interest costs. Now for January, we know we didn't have a loan in December, so we don't have to pay back a loan in January. However, in February, we may have to pay back a loan. That is, we may have to pay back the loan we took out in January, plus, okay, 1% interest. So I'm going to set up the formula to say the loan amount we took out in January, which will never be less than 0 because of the max function, times 1 plus the loan interest amount is how much money we will have to pay back in February. That is, we'll have to pay back $149,000 plus 1% as costs to pay in February. Okay? So I need to make sure when I add here, when I'm adding up revenues and subtracting costs, I also subtract the loan interest cost. So in January, there's no loan to pay back, so we're okay. In February, we're going to have a loan to pay back, obviously. Okay. Now, we'll call this the ending cash amount. So what we will end each month with in cash is our revenues minus our costs, that is the true amount of cash, plus any loan we take out. So if we had to take a loan out, we'll take a loan out. The idea is we should never end the month with any cash less than $250,000. Okay. And now we know in February what our beginning cash amount will be. It's the ending cash amount from January. All right, so we'll work through that fairly quickly. So we'll go through just one more time. Assuming we know January sales amount, we can compute January material cost amount. That is, 80% of those sales we'll have to pay in cost to build the thing we want to sell. Okay. We also know our fixed cost. That was given, but we copied it down here, easy enough. Okay. Our fixed costs are known. And we may also have loan interest costs. That is, we may have to pay back a loan with interest, although in January we know we don't. We know we haven't taken a loan in December, so we know in January there's no loan interest cost. We know how much cash we start the month with. We know how much sales we made last month. Okay, so in January we know we get as revenue coming in sales amounts from December, okay, which in this case is $1.54 million. Okay, and we know how much, based on how much cash we started with, we know how much interest our bank account earned, basically on that cash. So the cash we had in the bank, interest we earned from our bank for that. So now we can compute, so we know how much cash we started with, how much cash came in from sales from last month, and how much cash we earned from our bank, or how much interest we earned from our bank. We also know how much costs we had to pay, material cost, fixed costs, and payback of any loans. So we can basically compute all those revenues, all those cash amounts we had come in, minus all the cash amounts we have to pay out, costs, and we can compute that. And now we can compute from that whether or not we need a loan. So if that amount is less than $250,000, we need to take a loan for whatever the difference is, so we can have $250,000 in the bank at the end of January. If this amount, revenue minus cost, is greater than $250,000, okay, then we don't need a loan. So this max function basically ensures that we'll never take a loan for less than $0. That is, we'll never try to unloan any money. Okay, and so whatever cash we ended with plus whatever loan we need to take gives us the ending amount we'll have in the bank at the end of the month, which now becomes the beginning cash for next month, and so forth. So now we should be able to copy these formulas across, assuming I did them all correctly. Have all this computed. So in February we started with $250,000 in the bank again. Okay, we had our January sales numbers, our invoices from January got paid, so we got 1.8 million coming in. We got the typical, 1,000 $250 of interest come in from the cash we had in the bank. We had to pay $1,200 in material costs, plus fixed cost of $250,000, plus loan interest costs. So we had to pay back the $149,000 loan plus 1% interest, so roughly $150,000. So all of our revenues in February, cash coming in minus costs going out, ended February with $451,000, okay, which was more than the minimum amount of cash we want to keep on hand. So we need no loan in February, which means we just end February with $451,000 in the bank. So now we start March with $451,000. Well, in March we have February sales come in; they get paid. We have the interest we earned from our bank, 0.5% of $451,000, so $2,000 plus. We have our material costs in March, our fixed costs, and our loan interest. Well, in March we have to pay no loan back. We didn't take a loan in February, so we don't have to pay anything back in March. So we can compute all of the money that came in minus all the money that goes out, and technically March we would end with $33,000, which is less than we want to, so we'll take a loan out for $217,000, so that we end March with our minimum amount that we ever want to end with, which is $250,000, okay, and so forth. So it keeps going on and on. So this is our model. Now, we did want to compute a few things. We wanted to know the maximum loan amount. Okay, so here I'll just compute that as the max across all these loan amounts. So for all 6 months, what was the maximum loan we took out? It was $648,000. Okay. We also wanted to know the amount of interest we had to pay back. So loan interest that we had to pay. We could have computed that directly, but I didn't. So let's just say for that we will take all of the paybacks, the sum of all that, the sum of all the loans we paid back minus, the sum of all the loans we took out, and that'll basically tell us how much interest we paid. So how much did we end up paying back minus how much we took out was the amount of interest we had to pay overall. So we had to pay $12,000 in interest on all those cash loans we made or took. Okay. All right. So those are two things we were interested in. I'm just going to, not that these are values we're going to optimize, but I'm just going to highlight those in green so we can see them. Okay. All right. Now, the one thing we did not do was handle the uncertainty, which is we don't know how much sales we'll make in those 6 months. We have parameters for some randomly distributed projections, but we didn't use those yet. We just assumed we'd always sell the mean. Now, what I'm going to do is we're going to start using the Analytic Solver platform's feature that allows us to represent these randomly distributed values. So here in cell D14, I'm going to insert from the Analytic Solver platform tab in Excel, under the Simulation Model ribbon, a new distribution. That is, I'm going to insert something that says, I don't know what value this will be, but I have a distribution of values. That is, a randomly selected value from this distribution is what I suspect the value is. Okay, and I'm just going to use under the common something called the normal distribution. Okay, we can talk more about some of these other distributions another time, but for now we're just going to use a normal distribution. And basically a normal distribution works in the following way. Okay, it has two parameters, a mean and a standard deviation. The mean is the most likely value, the common value, and that in this case that's going to be the value taken out of cell D3, the January sales mean value. Okay, so that basically says we expect we'll sell $1.8 million. The standard deviation says basically how widespread is the range of true values going to be. So we think it'll be 1.8, but it may be more or less. How much more, how much less is governed by the standard deviation, which we were told is in cell D4, so $80,000. So by setting those two parameters, okay, and I'll show you other ways you can set them, but by setting the mean and standard deviation parameters for this normal distribution, you can see here a graph that says what value that cell might take on. So this blue graph is basically the likelihood of any particular x value. So the most likely value is going to be the one here in the middle, $1.8 million. It may be as low as, it looks like, somewhere between 1.5, 1.6 million. It may be as high as about 2 to 2.1 million, but those are really unlikely. Okay, we think it'll be somewhere probably most closely to 1.8. Okay, so I'm going to save that. So you'll see here in this cell, it's computed a new value. So the actual January sales numbers right now, it's randomly guessed will be something like 1.743 million. You can see from the equation up here, okay, that it's using this function PSI normal for a normal distribution. The mean is in cell D3, the standard deviation is in cell D4. So these are the mean and standard deviation which govern that normal distribution. It merely says it's going to be a value, we think, close to 1.8, but it may be up to 80,000 plus or minus, or even beyond that, just with a very low likelihood. Okay. All right. So every time we recompute, and I forget the Excel key to hit for that, but every time we recompute values, it'll compute a new random value here. So now it's computed 1.8. If you double click on this cell, you can get back to that distribution chart that shows you both the parameters and visually what values that means it'll take on. Okay. All right. Now that I've put in this random function, okay, this function that's going to compute a random value subject to these parameters, so somewhere close to these parameters, I'm going to copy that for all the rest of the months. So every month is now, its sales number is now a randomly chosen value close to its mean plus or minus its standard deviation. Okay. All right. And actually, I'm not sure where this base case thing came in, but we won't worry about it for now. So you can see here the February sales number. I can double click on that and see the chart. This February sales number are going to be somewhere around 1.5 million plus or minus, what was it, 80? Yeah, plus or minus 80. So it may be very unlikely, but it may be as low as about 1.25 or as high as 1.75, but it's most likely going to be somewhere between about 1.4 to 1.6. All right, so now we have uncertainty in the model. That is, we have randomness injected into our model. So now what we want to do is basically compute new random values for each of these cells over and over again and find out what maximum loan amount we'll need for those randomly selected sales numbers. However that computes out, what's the maximum loan we might need? Okay, so we want this maximum loan amount now to be sort of the objective, and we want to know what values can it take on? What values are likely to be found in here given random values chosen up here based on likely values that are there, right? So each one has a mean and a standard deviation. If we readjust these over and over, it'll change the maximum loan amount. So we want to know, how does that change? Specifically, what we'll do is we'll do 1,000 simulations. That is, we'll recompute this 1,000 times for 1,000 different set of sales numbers and 1,000 different maximum loan amounts, and then we'll show a chart, basically a blue chart like we've seen already, to say what values that could be. Before we can do that, though, we need to tell the analytic solver platform that this cell, D25, the maximum loan amount, is the cell we're interested in charting or seeing a chart for. So all I'm going to do is highlight that cell, click the results button, output, and say that the output is in this cell. Okay, so the output that I'm curious in seeing graphically displayed is in cell D25. You'll see what that really does when I've clicked that button is it's added to cell D25 in the equation for it. It's just added in this PSI output function. Okay, I don't know how that works, by the way, but that's how it works. And now you can see as all these values change, how will cell D25 change? So what we're going to do, we're going to use the Simulate button on the Analytic Solver Platform tab, and we're just going to say Run Once. Okay. Now, we say Run Once, but what that means is run one set of simulations. By default, it will do 1,000 simulations. So in whatever time that took before this came up on the screen, it recomputed 1,000 different sales numbers for January to June and how much of a maximum loan we had to take out. And now it's graphed those values. So you can see sort of a range visually depicted. What's the maximum loan amount we might have to take? Well, we think it will be somewhere here in the, I don't know, $650,000 range. That's the most likely value. But it can go as low as, well, less than $400,000. And it can go as high as something like, I don't know, maybe $1 million. If you look over here to the right-hand side, you'll see specific numbers. So the mean, the expected number, is about 648. If you remember, 648 is what we saw when we actually had the mean sales numbers hard-coded, right, in the sale, in the January through June sales. So that's kind of what we expected, is if we sold on average, the average amount each month, we would need a maximum loan amount, I think it was from April, of $648,000. So that's what we simulated as well. Standard deviation, now we know we might need plus or minus about $104,000 from that, usually. Okay. However, we might go as low as, so in 1,000 simulations, the lowest maximum loan we ever took was $357,000. The maximum we ever took was $987,000. Okay, so there's a range between those two of about $630,000. Okay, and so forth. There's more numbers in here. A lot of the rest of these numbers have to do with more advanced and very specific statistics that we're not going to worry about, okay, for this class. But just reading these sort of basic statistics, we can say first that we expect to take a maximum loan of about, say, $650,000, okay, $648,000. But we may take a maximum loan for as little as $357,000 or as much as $987,000. Now, there's one other thing we wanted to answer on this question, which was what is the likelihood that we'll need a loan for more than $750,000? That's our credit limit. We wanted to know what's the probability or the likelihood that we'll need more than that on some month. Now, to answer that question specifically, the easiest way I found to do that is you can see on this chart here, there's 3 different sections, okay, and 2 different values listed here. What these are telling me is that between a maximum loan between $475,000 and $829,000 is 90% likely. That is, it's 90% likely. 90% of the time we'll need a loan between those 2 amounts. It's 5% likely we'll need a maximum loan less than $475,000. And it's 5% likely we'll need a loan more than $829,000. Okay? So if I wanted to know what's the probability or likelihood I need a loan more than 750, I can just click on this number up here and it'll allow me to change it, say to 750, and you'll see that it's moved the red line and recomputed numbers to say basically the likelihood or the percent chance you'll need a loan more than 750,000 is 16.1%. That is, there's a 16% chance we'll need a maximum loan amount more than our credit limit allows us to take. Okay, based on the 1,000 simulations we just did. Okay. Now we might also ask questions like, well, what's the likelihood we'll need a loan less than, say, 500,000? So maybe I can make this lower bound 500,000, and we can say, well, the likelihood that we'll need no more than 500,000 is 7.6%. Okay. You can also click and drag these bars to sort of get whatever values you want. Usually if you have a specific value in mind, it's easier to just type it in, but you can also enter values for the percentages. So we might want to say, what's the maximum loan amount we need? I'm sorry. What's the minimum max loan we would need with 10% confidence? That is, if I set this value to 10%, that just means with 10% chance I'll need less than 513,000. With 90% chance I'll need more than that, right? So there's a 90% chance now that I'll need more than 513,000 because there's a 10% chance I'll need less than that. Okay. So all sorts of ways we can ask those kind of questions. This chart is basically the best way you can get answers to all of those. Okay. So again, we set up the model. We set up which parameters in the model are uncertain, that is, are governed by some random value that we have an idea of what it might be, but we're not sure, right? There's uncertainty what value it really will be. So we simulated 1,000 different cases of what values it could be and took from that 1,000 different outcomes, in this case of the maximum loan amount we need. And now we can play with these numbers to answer questions like the maximum loan we'll ever need, the minimum loan we might ever need, minimum max loan we'd ever need across all the months, the likelihood we'll need a loan more than a certain amount or less than a certain amount, okay, and so forth. Okay. I'm going to close this screen and then show you how to get it back in case you ever do close it. So now that we've simulated 1,000 entries and we've told it that we're interested here in cell D25, it's the one that has the PSI output function in it, which we got from clicking result button. If we just double click on this cell again, without rerunning all those 1,000 simulations, we can get the chart, okay, to see again. So same thing we were just looking at. We can ask questions like 750,000. That's 16.1% likely you'll need more than that, okay, and so forth. Okay. That was a long-winded example. Are there any questions about simulation in Excel? Okay. I'm going to back up for a second and remind us all. The reason why we have simulation as a technique is because there's uncertainty in our model. That is, there's values we don't know for certain. There's values we have maybe guesses at, a range of values we think they could take on with certain probabilities, but we don't know for certain, and so we need a way to account for that uncertainty. That is, we need a way to answer questions about the objective, the output, in this case maximum loan amount, or we could do the same if we wanted to use the output as loan interest paid. But we need to say something about that value, not just what value we think is most likely, but the range of values it could take on, given that we have uncertain parameters that have their own range of values they can take on. So let's do another quick example, same model. Instead of making the output the maximum loan amount, I'm going to make the output result that we're interested in the loan interest being paid. Okay, so now I've made that cell the one that has PSI output in it, and I can double click on that cell. What you'll see now when I double clicked on that cell to open the chart is it said you haven't done your simulation yet. That is, now that you've changed what you want to see, you need to re-simulate everything. And so you can just say yes, and again it will do 1,000 simulations. That is 1,000 different values for the sales numbers. And now we're looking at the distribution of the loan interest we'll have to pay back. Okay, so on average we think we'll pay back, $12,000 of loan interest. At minimum, we think we're going to still having to be take so much loan amount out, even if we had high sales numbers. That is, we were selling things at a high rate, getting lots of money coming in. We still think that at a minimum we'll have to take out loans and pay back about $8,000 in interest. At maximum, we'll be paying about $17,000 in interest on our loans. Okay, so we know that range is just 9. And we can, again, play with the percentages and values up here to say something like, what's the likelihood that we'll pay back more than $10,000 in loan interest? Okay, so I can look at this value here, $10,000. There's a 5% chance we'll pay back less than $10,000, which means there's a 95% chance, just 100 minus 5. 95% chance we'll pay back more than $10,000. Okay. If I ask the question, what's the likelihood that we will pay back $11,000 or more in interest, then we can change that value over here to 11 and see that it's 15.4% likely we'll pay back less than $11,000, which means it is what, 84.6% probable we'll have to pay back more than $11,000, okay, and so forth. Okay, one last thing I'll show, and then we'll take a short break. So we see here the distribution of, in this case, loan interest paid back across all the 6 months. We might be curious in knowing which part of our model affects the amount of loan interest paid back. Okay. That is, what's the driving force behind how much we're having to pay back in loans? Is there some part of the model that is affecting this amount, this output, more than other? And to do that, I'm going to look at this sensitivity tab. Okay, instead of the frequency tab, I'm looking at the sensitivity tab. Now, what the sensitivity tab tells you is for a set, I guess I would say a set percent change in certain cells of the model, what was the percent change in the output? That is, loan interest paid. Well, that was on average about $12,000. Okay. If cell H14 changes, that is, if cell H14 goes up by, I think it's 10%, then the loan interest amount we have to pay goes up by 0.69%. Now let me drag this out of the way. Let's see, what is cell H14? H14 looks like it is the sales numbers for May. Okay, so the sales numbers in May highly affect, more than maybe any other cell, how much loan interest we have to pay back. Okay, the sales numbers in May. Probably the reason that is, and I'm just going to kind of give a best guess here, is our maximum loan comes out in April, and so what we sell, well, let's see here, what we sell in May, I'm sorry, the maximum loan usually comes in about April. So what we get in May maybe affects how well we can pay that back. I don't know. What you can also see is cell G14 also highly affects the amount of loans we pay back. Well, G14 is the sales numbers in April, obviously. Okay, so the sales numbers in April govern how much of a loan we usually have to take in April. Okay, which means the more you can sell in April, right, the less of a loan you'll have to take out. Okay, so sales in April affect the amount of loan interest to be paid back because it affects how much of a loan you need to take. Okay, and so forth. So E14, actually E14 being the sales amount in February, affects the interest amount paid in a negative way compared to these other two. So the less we sell in February, the more loan interest we'll pay back, okay, and so forth. So you can kind of see these values are telling you basically how much of an effect that cell has on the output, and it's ordered them or ranked them here as the cells that most affect it down to cells that affect it less. Obviously there's more than 6 cells that affect the output, but by the time you get to cells that affect it beyond these 6, the effect is going to be really small. Okay, so basically what this is saying is there's a few cells, maybe these top 3 here or top 4, which are highly affecting the amount of loan interest you're going to have to pay back. Beyond that, any other individual cell, individual calculation or individual sales number or material cost number or whatever it is having a negligible or very small effect. Okay, so this sensitivity tab can help us answer questions like, what is the driving force behind this output? That is, what affects how much loan interest we have to pay more than anything else? And the answer here appears to be the sales numbers in, what was it, May, and the sales numbers in April, okay, are definitely the 2 highest things that affect that, and so forth. All right, so that's the sensitivity tab. We've been looking at the frequency tab, which is the probability of any individual value or the individual range of values of the output. The other tabs are basically different forms of looking at all that same information. Okay, cumulative frequency and reverse cumulative frequency are just a different form of this same chart. And scatter plots is basically a different way to visualize some of that same data. Okay, mainly I'm going to be giving you assignments or asking questions on the final or anything that are directly come from either this frequency tab, okay, or maybe this sensitivity tab. Okay, in terms of figuring out the range of output values or the probability of any given range or given amount. Okay. All right, let's take a break. We'll take a short break, come back, talk a little bit more about simulation, do another example, okay, so you can see how another example would work, and then probably end the night talking about the upcoming final exam and what will be covered on it.